Hi children, how are you? I hope you are doing well. This is Sudhir Kumar from Sudhir Physics classes. Today we are discussing about the neutral points. Neutral points due to a current carrying conductors. You can obtain neutral points due to electric fields. In electrostatics also you will discuss about the neutral points. When the fields are produced due to the charges between like charges and unlike charges, you will be finding the neutral points. Similarly, you will be finding the neutral points in the case of magnets, poles, etc. And here we are finding magnetic neutral point due to the current carrying conductors. You know, current carrying conductor will produce a magnetic field around it. And the magnetic field due to the infinite long conductor is given by mu naught I by 2 pi r. R is a distance. And the direction of magnetic field is determined by the right hand thumb rule. This indicates the direction of current, and this indicates the direction of magnetic field. That formula and this direction you are supposed to know, which we have done already in previous classes. So let us consider now two current carrying conductors, infinite long current carrying conductors. So this is a one infinite long current carrying conductor, and let the current in this is I1. There is another infinite long current carrying conductor. Let the current in this is I2. So these two are separated by distance r. Distance r. This current carrying conductors, both, they produce magnetic field in this vicinity. So whether you consider this region or this region or this region, there will be magnetic fields produced by the both conductors. So here you will have both magnetic fields. Magnetic field due to first conductor, magnetic field due to second conductor. Both will be present here. Similarly, here also magnetic field due to first conductor and due to second conductor will be present here also. Here also both, B1, B2, due to first conductor, due to second conductor. So like this, the magnetic fields are present here. Okay. So our aim is to determine neutral point. At the same time, you will find the resultant magnetic field also. What is a neutral point? Where the resultant magnetic field is zero, then such a point is called neutral point. So in fact, you must be able to know how to find the resultant magnetic field. So first of all, the magnetic field produced by this current carrying conductor of infinite length is given by mu naught I divided by 2 pi r. R is a distance. You should know this formula. Now let us say in this region I would like to find the magnetic field now. Say at some distance x, I would like to find, this is not a midpoint, somewhere I would like to find the magnetic field here. Resultant magnetic field here I want to find. This is at a distance x from the first conductor. So naturally this will be at a distance r minus x from the second conductor. This point is x from the first conductor and r minus x from the second conductor. So here the first conductor will produce a magnetic field. Direction of magnetic field is decided by this rule. This indicates the direction of current and this will indicate the direction of magnetic field. So therefore the magnetic field is inward due to this conductor. So inward means I'll take like this. This is called B1. B1. So the magnetic field B1 is how much now? I told just the formula now. Mu naught I1 by 2 pi r. R means distance from the conductor where you are determining the magnetic field. So what is the distance? X. Next. It is inward. It is inward. Good. Coming to this. I told everywhere there will be two magnetic fields produced by the two conductors. So one more field is there. So this is a current carrying conductor. The field will be coming out here. So here field will be, I will be having an outward field here, B2, due to the second conductor. How much is this B2? Same formula I will use. Mu naught I2 divided by 2 pi. Distance is r minus x here. The distance is r minus x here. Now these two fields are at 180 degrees. That means these two fields are opposite to each other. One field is inward due to the first conductor and another field is outward due to the second conductor. So that there will be two fields now like this in opposite direction. One is inward and one is outward. So they will be at 180 degrees to each other. So if you want to find a resultant field, you have to subtract these two fields. You know parallelogram law of vectors. When theta is 180, the resultant is P minus Q. So P minus Q, like that. Okay. So the resultant field here, let B is a resultant field. So I have to subtract these two. B1 minus B2 I will do. B1 minus B2. Mu naught by 2 pi is common. In bracket, I1 by x, right? Minus I2 divided by r minus x is the resultant field at in this region. This x can be a variable distance. If you move the right side, x increases, r minus x decreases. If you move left side, x decreases, r minus x increases. Somewhere you are finding the resultant magnetic field. Now what is the direction of this resultant magnetic field? Already I said the B1 is inward and B2 is outward, isn't it? Right. Resultant field. Suppose I'll write here difference here. Let me write the difference. Suppose if B1 is greater, the value of B1 is greater than B2, then give the resultant field that sign only. That is inward. In case if B2 is greater than B1, if we calculate, then the greater field is this. So for that, the resultant field must be given this answer. So depending on which is greater, you can give your answer. This is a resultant field all the time. Now, if this is a neutral point, what is a neutral point? The point where the resultant magnetic field has to be 0. They will be equal and opposite, and they will be cancelling. They will be equal and opposite. Okay. Sorry. So the resultant magnetic field is 0 means this everything equated to 0. This everything equated to 0. Okay. That means this will go that side and become 0. That means I1 by x minus I2 by r minus x is equal to 0. This is nothing but I1 by x is equal to I2 by r minus x. Let me do it here, remaining part. I2 by I1, r minus x by x. So this is r minus x divided by x is equal to I2 by I1. So this is nothing but r by x minus 1 is equal to I2 by I1. I wanted to find x actually. Where is the neutral point located? So this is nothing but r by x is equal to I2 by I1 plus 1. So now cross multiply and find x now. That's it. So x is equal to r divided by I2 by I1 plus 1. This is the distance where the neutral point is located between the current carrying conductors. Because the resultant field is 0. This resultant field is 0. Then I would say equating to 0, I solved for x. That means I solved for distance of the neutral point from current I1. So there is one important point to be discussed. You should know the I2 value and you should know the I1 value and you should know the distance between the conductors. Then I can find the distance of the neutral point. That is clear. No confusion at all. If you don't remember the formula, I can directly, you can equate the two fields here. Resultant field is equal to 0. No? You can equate B1 is equal to B2 and solve the problem many times. So one point I want to tell you. Here always please take greater current as I2 when you are using this formula. Let's say I2 is greater than I1 always. I2 must be greater than I1. And X is always measured from smaller current. X is always measured from smaller current. Suppose he wants where is the neutral point located from second conductor. Okay, already you will determine X. And from this R, if you subtract this X, I'll get the distance of the neutral point from the second conductor. So, whatever the question he asks, whether this neutral point is measured from first conductor or second conductor, see the question properly. Understand? So, first you will be determining X. If you want R minus X also, you can determine because R value will be given. And this distance will be smaller. See, neutral point is always nearer to the smaller current. The neutral point is always nearer to the smaller current. So these 2 points are very, very important. So finally, there is a neutral point here somewhere at a distance x, which is given by this relation. And if this is not equal to 0, you will get some value here, isn't it? You can find the resultant field always. So now let us, this is the in between. You can find a resultant field like this. Or you can also find the neutral point by using the condition resultant field equal to 0. So in between concept is over now. We will go to the right side part. In this region, the right side of the both conductors, I would like to find the resultant magnetic field. Then how will I have to find the resultant magnetic field in this region and in this region? That is my aim here now. Let us say in this region, somewhere I want to find the magnetic field. I told that there will be 2 magnetic fields here, one due to the first conductor and one due to the second conductor. We have to find both the fields and add them vectorially. Very simple, in their same direction, you just add them. If they are in opposite direction, subtract them. For time being, it will work out for you. Now at a distance x, I will take again at a distance x. Here I wanted to find the magnetic field in that region. So magnetic field due to the first conductor at this point I want now. So this is a current is moving in upward direction. So the magnetic field will be inward here. So the magnetic field will be inward here. So inward. So there will be an inward magnetic field here, B1. How much is this B1? This is mu naught I1 by 2 pi distance. What is the distance from the first conductor? Already R plus X. The total distance is R plus X. That is the magnitude of the B1 and it's directed into the board. Now this conductor also produces the field here always. So this field is also inward. Both fields are inward only. See, this is also inward. So another field, inward field is produced. Okay. This is B2. B1 and B2. And this B2 is given by mu naught I2 by 2 pi. This distance I am taking x now. This part is over. Okay. This is x. And this is also inward. See, both fields are acting inward. So just add them to get the resultant field. So therefore, the resultant field over this region is equal to sum of these two. That is mu naught by 2 pi into I1 by this one, R plus X, plus I2 divided by X. Because both are acting inward, the resultant field is also inward. So when two fields are acting in same direction like this, there is no question of cancelling these two fields. So you will never get a neutral point on right hand side. If they are in opposite direction only, there is a possibility of the fields getting cancelled and getting the neutral point there. So you can never get the neutral point on right side, especially when currents flowing in same direction I am discussing. Okay. Now let us come to this side now. Okay. So this side also I would like to find the magnetic field, say at some distance x from the first conductor. Let this distance is x now. Say the first conductor will produce an outward field here. So outward. So I will be getting an outward field here. B1. How much is this B1? Mu naught I by 2 pi distance. Now this second conductor also produces field now. See, left side it will be producing an outward field. Outward field. So outward, outward, outward. So this B2 is also outward field. This B2 is equal to mu naught I2 by 2 pi. What is the distance from second conductor? Already this is R and plus X. The total distance is R plus X. Fine. Here both fields are acting outward. So again these both are in same direction like this. There both fields are like this. Here both fields are like this. So what is the resultant field means? B is equal to, add them. So this is mu naught by 2 pi, okay, into I1 by X plus I2 by R plus X. And the resultant field will be outward. That's all. So here the field is always inward. This is the resultant field on the right side region. And here the field is always outward. This is the resultant field in this left side region. There is no question of getting neutral points in this region because the fields are acting in same direction, especially when currents are in same direction I am talking. And you will be getting only one neutral point between the two current carrying conductors at some distance. Okay. And that neutral point can be calculated. I have already derived the formula. So here if you want to find a resultant field, you have to subtract the fields. And if in this region you are finding a resultant field, you are adding the fields. So this is about the neutral point when currents are in same direction. Now if I reverse the current in one of the conductor, what about this neutral point? What will happen? You can just think. You can just think, isn't it? See, if one of the currents is reversed, anyhow when current is reversed, the direction of the field also gets reversed. Magnetic field direction. Suppose if it is inward, if you reverse the current, it becomes outward. So one of the conductor's current I am reversing. So one of the field will be getting reversed. So we will get a different situation here. So let me take now, here is, this is one of the current carrying conductor, infinitely long. This is another current carrying conductor. Now the current I am taking downwards. I am taking downward current now. So same, again in these three regions I wanted to find the resultant field. Again in these three regions, region 1, region 2, region 3, you will have two fields. Field due to the first conductor, field due to the second conductor. We should add them, vectorial sum. Here also field due to the first conductor, field due to the second conductor. So you have to add them, vectorial sum. Here also field due to the first conductor and field due to the second conductor, vectorial sum. As we done in the previous class. So let me take now between. So let this distance is R, distance between the conductors. Now somewhere at the distance x, I would like to determine the magnetic field. Resultant magnetic field I would like to determine. And this point is located at a distance x from the first conductor and at a distance r minus x from the second conductor. Now the field due to the first conductor is inward. So I'll be getting inward field due to the first conductor. And now this current is reversed. So I will be getting here field inward. Inward only. So the second field is also inward. B2. So what is the resultant field here means? The resultant field here is always B1 plus B2. That's it, very simple. So there is no question of getting neutral point between the conductors. So wherever you find, always the two fields are in the same direction, the two inward, and hence they will be always added up. You won't get any neutral point. And what is the resultant field means? We can substitute now. What is B1 means? Mu naught I1 by 2 pi x. What is B2 means? Mu naught I2 by 2 pi into r minus x, and on the whole field will be inward. This is your answer. Let us go that side now. So if I go this side, let us say at some distance x only I will take. So at some distance x from the second conductor, I would like to determine the resultant field. Now, because let me take the first conductor. So this first conductor produces a field in this region, definitely. So now right side it will be producing inward magnetic field like this. So the magnetic field is inward. This is B1. Let me write what is B1 now. So this B1 is equal to mu naught I by 2 pi distance of the point. This point is located. This is R and this is X, right? So R plus X. So this will be R plus X. What is the direction of field? Inward I got. So this is inward field. So first conductor's field is over. Now let us come to the second conductor's field. Now this is the current is going down. I want the field on right side, no? Like this. So field is coming outward here, outward. So I am getting an outward field. B2. And you know this B2 is equal to, how much is this B2 equal to? Mu naught I2 by 2 pi. From the second conductor the distance is x. But one thing, always B2 will be greater than here. Whatever the position you take, always B2 is greater than B1 only here in the right side. Always B2 is greater than B1 only. Just think why. I told that whenever you are calculating the neutral points, you please take that I2 is greater than I1 and distance x of the neutral point is always measured from the first conductor, and the neutral point is always nearer to the first conductor. When I said nearer to the first conductor, this side only you will get. Okay, that is nearer to the second conductor. So nearer to the second conductor, nearer to the greater current, you won't get neutral point. Nearer to the smaller current only you will get neutral point. That answer I already gave you. But why you will understand here now more clearly. Now if you come over here. B1. This is a formula. But current is less than I2. Therefore, and B1 will be less than B2. It has to be because the current is smaller. I2 is smaller than I2. Next. Because you are going far from the first conductor, so this distance is more from the first conductor. Again, field decreases. So the numerator I1 and denominator R plus X are decreasing the field B1 compared to B2. When you come to B2, current I2 is greater. So it produces a greater field relatively. And the distance x is smaller, you are nearer to the second conductor. So that is also enhancing the field. I2 is enhancing and x is also enhancing the field. That is why at any point you take, B2 will be always dominating. There is no question of cancelling. The resultant field will be always acting outward here. And because these two are at 180 degrees, the resultant field is nothing but B2 minus B1 is fixed answer. Because this is always greater. And you know, outward field is greater. So the resultant field will be outward. Substitute B1 and B2 there. So there is no neutral point here and there is no neutral point here. And there will be a neutral point here. And what is the condition I told you? Neutral point is nearer to the smaller current. Yeah, it has to be here then. And x is always measured from here. When you are calculating neutral point, I told, okay, x is measured from I1. So let me take now another point this side also now, in the left region. So let this distance is x. And here I would like to find the resultant field. So field due to the first conductor. Right, field due to the first conductor. See, this is a field due to the first conductor. Outward, 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 outward. So I'll be getting outward field. This is an outward field. Okay? Outward field. Now, how much is this outward field? You know already the formula, isn't it? B1. is mu naught I1 divided by 2 pi x. 2 pi x. And it is outward. Outward means dot. What about this? Oh, this. This is a current and this is field. Inward, 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 inward. So I am getting B2 inward field. B2 inward field. How much is this B2 now? B2 is equal to mu naught I2 by 2 pi R plus x. This is R plus x. This is the total distance from second conductor. Observe here. The current I2 is greater than I1. So this must produce a greater field. But R plus x is greater than x. So this must produce a lesser field. So one is enhancing the field, one is decreasing the field. So there is a chance of compensation here. There is a chance. But here both factors are enhancing the field here. So always B2 is greater than B1 only. Therefore, if you want to find a resultant field, angle between B1 and B2 is 180 degrees. Then subtract these two, you will get a resultant field. If that resultant field is 0, then this can be a neutral point because you are getting opposite fields and I2 enhances the field, R plus x decreases the field. This is more, distance is more, field will decrease. I2 is greater than I1, then field will increase. So this is compensating here. Okay. So then we can get a neutral point at some distance x here. So for neutral point, let us erase this for solving. For neutral point I am solving now. So I want to find here and this is taken as neutral point here, right? So if this is a neutral point, the resultant field must be 0. These two will be getting cancelled. So the magnitude of B2 and magnitude of B1 are equal. So this is, I'll take mu naught I1 by 2 pi x is equal to, this is mu naught I2 by 2 pi into R plus x. I will take. So this mu naught gets cancelled. 2 pi gets cancelled. Then I2 by I1. I2 by I1 is equal to R plus x divided by x. Therefore, I2 by I1 is nothing but R by x plus 1. Therefore, R by x is equal to I2 by I1 minus 1. Just cross multiply. Therefore, x is equal to R divided by I2 by I1 minus 1. This is the distance of the neutral point from the first conductor. What is the distance of the neutral point from second conductor? X already you have determined. No, add this R. So R plus x is a neutral point from the second conductor. So this is how we will get a neutral point. So in this case, there is only one neutral point that is on left side, that is nearer to the smaller current. In other two regions, the resultant field can never be 0. This is the case when currents are in opposite direction. So this is about the neutral points due to the current carrying conductors. At the same time, you are also learned how to find a resultant field also. So thank you very much.